Okay, welcome again to Math 315, Analysis and Topology, and we're in Chapter 5 or Section 5, and we've been looking at the intermediate value theorem, or more correctly a corollary to that. And the idea there was that if you have a function that is continuous on some interval, and if you can find an a and a b so that p of a and p of b have opposite signs, then there must be a zero, there must be a real root of that function somewhere in the interval ab. You need, of course, the conditions are that you need the function to be continuous. And I mentioned that we could use this intermediate value theorem in order to find roots of functions. We can also use it, and this is a very nice application, we can also use it to prove that certain equations have a solution, especially in instances where you can't explicitly write down what the solution is. And so I'm going to do an example of that here. We're going to use the intermediate value theorem to show that this function, this equation I should say, e to the minus x equals x, has a solution. Now you might like to play with this, but there's no easy way of actually finding the solution of this. You can try taking logarithms, but it doesn't actually help you greatly. There's no elementary way of finding the enclosed form, the solution of this equation. You can get approximate values to the solution, and we're going to prove that it does have a solution, but to actually explicitly find it is very, very difficult. So here's the worked solution to this example, and there's several more in the tutorial problems we'll have a look at later. Just to have a look at it graphically firstly, just to convince you that it does in fact have a solution, at least graphically. If we draw the graph of y equals e to the minus x, looks like this. Of course it cuts the y-axis here at 1. And y equals x is this line through here, and you can see graphically that it's pretty clear that these two do intersect each other somewhere, which is this point here. But exactly what the x-coordinate of this is very hard to determine. And all we're going to do here is to just prove formally that there is a solution to this equation. And the way we do it is we need to get functions into the story, so we look at the difference between the two. So I've chosen to take x minus e to the minus x. I could have chosen e to the minus x, it doesn't matter. You just take all the terms onto one side, and I'm going to call that new function f of x. The first thing we just observe is that f is continuous, CTS. f is continuous because it's just a combination of continuous functions, and therefore it is continuous. And what I want to do now is it looks from my picture here that on one side, these are going to change sides somewhere between 0 and something. And so I'm going to start off with f of 0 and see what the value of that is. So if I put x as 0 in, then f of 0 is 0 minus e to the 0. e to the 0 is 1, so I just get minus 1, and that is negative. And that is negative, which sort of makes sense because I'm really subtracting this y value minus this y value. You see you'd expect to get a negative. Now I want to find something on the other side, so I'll try 1. You could try 2, it doesn't matter. I just tried 1, see what happened. And so I put x as 1 in, and so f of 1 is 1 minus e to the minus 1. Now for this one I had to use my calculator here, and I worked out 1 minus e to the minus 1 is approximately 0.632, and whatever it is, it's positive. So graphically that means this 1 must be over here, so we're subtracting this 1 minus this 1, we get a positive number this time. So I've got a function which is continuous. f of 0 and f of 1 have opposite signs, one negative, one positive. And so by the intermediate value theorem, so f has a 0 in the interval 0, 1. I should say here by intermediate value theorem. I should quote the theorem we're using. So by IVT, by the intermediate value theorem, f has a 0 in this interval. That means that at some particular point, this function takes the value 0. So x minus e to the minus x has a solution somewhere in this range. In other words, taking it back on the other side, e to the minus x equals x at this particular point. So that's a nice little application of the intermediate value theorem to prove a rather complicated equation which we can't solve analytically actually indeed does have a solution. The next example I'm going to do is a little bit more difficult, but it's a nice theoretical application of the intermediate value theorem to a slightly more abstract problem. So we have a function f which is continuous, and it's defined on the interval 0 to 1. And we're told it also has its range also somewhere in the interval between 0 to 1. So it's defined from 0 to 1, and the output values lie somewhere in the interval on the y-axis from 0 to 1. And we want to prove there is a real number c somewhere in there so that f of c equals c. This point c is often called in mathematics what's known as a fixed point. So I've got a function. We're not told what the function is this time. We're just told it's continuous. We're told its domain. We're told that its range is somewhere in this interval. We want to prove that this f has a fixed point. That is, there's a point c where f of c equals c. This is a difficult problem. If you've not seen one of these before, it's quite hard to know where to even begin with this. So I'll take you through this fairly carefully. Here's the solution to this problem. These fixed point theorems, these fixed points are quite important in mathematics, in fact, which is why we're looking at it here. So here's my picture. So there's the interval 0, 1, and there's the interval 0, 1 on the y-axis. And we have a function, some sort of function that's defined on the interval 0, 1, and the range of it's going to be between this point and this point. And that's also somewhere in the interval between 0 to 1. Now, what does it mean to have a fixed point? Well, it means that if I draw the line y equals x, then that line is going to cut the function somewhere here, and this is the point c that I want to show exists. So at this point c, this y value will be f of c, because that's where it is on the y-axis. And also it happens to lie on the line y equals x, so if x is c, y is c. So this is the point where c equals f of c. And so we want to show that such a point exists. Now we have to worry just a little bit about what's happening at the possibly happening at the two endpoints, because I want to exclude these, in fact. So this is just a little technical point here. If my function happened to start here, if f of 0 was 0, well, in that case, I've finished, because I found a number c, which is just 0, so that f of c equals c. I just take c to be 0. So that's one possibility. Or, if it happened to go all the way up to here, if f of 1 was equal to 1, that's a possibility. Well, then again I'm finished, because now I've found a c. In this case it's 1, so that f of c equals c. So I begin by, if f of 0 is 0 or f of 1 is equal to 1, then we have a c in the interval, and I should say in the interval between 0 and 1, such that f of c equals c. So I've got a fixed point if either of these two things happen. So we're going to exclude those now. We've dealt with what happens if either of these happen. If neither of them happen, then that means my f of 0 was not 0. It had to be up here. It had to be bigger than 0. And if this doesn't happen, then my f of 1 has to be less than 1. It's going to be down here somewhere in the picture. So we'll keep those two things in mind. F of 0, I'm assuming now to be strictly bigger than 0, that is positive, and f of 1 is strictly less than 1. Now, as we did in the previous example, I'm going to introduce a function g of x. I'm going to put g of x now is f of x minus x. So we're trying to solve f of x equals x, so I'm going to take it on the other side and write g of x as f of x minus x. Now, what I'm going to check now is I'm going to evaluate this function g at the two endpoints, 0 and 1. I want to know what's happening to this function g now at 0 and 1. So I plug in 0. So I get f of 0 minus 0. Well, that's just f of 0. And my assumption was that f of 0 is positive. So at this stage, g of 0 is positive. Now I'm going to work it out at x equals 1, so I put 1 in, I get f of 1 minus 1. Now remember, f of 1 up here, by my assumption, was less than 1. F of 1 is less than 1. So if I take a number that's less than 1 and subtract 1, so it's going to be less than 1 minus 1, which is 0. So that says g of 1 then is going to be less than 0. That is, it's going to be negative. So I have this function g, where g of 0 is positive, g of 1 is negative. So they change sign. And g is continuous because it's f of x, which was continuous, and x we know is continuous. So the difference of two continuous functions is continuous. And so by the intermediate value theorem, g has a 0 at some point, I'm going to call it c, somewhere in this interval, and I should say by the intermediate value theorem, should always perhaps quote the theorem. So by the intermediate value theorem, this function g is continuous. It changes sign between 0 and 1, so there must be some 0 in between the two of these ones, i.e. g of c is 0. And finally we put the c back up into here. G of c is 0, so f of c minus c is 0, so f of c is c. Now that is a more sophisticated example. It's not one I'd expect you to be able to do instantly at sight, but it's a very nice example of the theoretical usages of this intermediate value theorem. So I want to talk now about maxima and minima, and we're talking about these globally. We'll look at what's called local max and min later, but we're going to talk firstly about global max and min. So we've got a function f defined on some interval a, b, and we say that f has a global maximum at some point c, also known as an absolute maximum, if f of c is bigger than f of x for all the other x's inside the interval. Now immediately let me just put a little picture here to explain that more carefully here. So here's my interval a to b, here's my function, and there's my global maximum. F of c is bigger than f of x for any other x in this interval. F of c is always bigger than f of x. So this is called a global maximum. Well, similarly, we can say that f has a global minimum at x equals c, also called an absolute minimum. That means f of c is less or equal to f of x for any x inside this interval. And again, looking at the picture, here's our function. There's the interval a to b. It might wobble around a bit, but you can see in this picture, this is going to be the global minimum. It's the smallest value the function takes. And so f of c is less than f of x for any other x you pick inside this interval. F of c will be less or equal to f of x, and that's called a global minimum. A point like this one here, it looks like a kind of minimum. We're going to call that later a local minimum. And similarly, this looks like a sort of maximum here, but it might not be. It depends on how high this goes. This might go a bit higher. But this would be, well, later on we'll talk about local maximum, where we limit our gaze a little bit and say, well, it looks like a bit of a bump here. It looks like a kind of maximum, but in fact the maximum might be over here. And we're going to call this a local max and a local min later on. Okay, so we're going to just do an example of this one. So we're going to look at the function f of x is x into x minus 1, defined on the interval 0, 2. And it has, well, here's the picture. So it's just a quadratic, or part of one, because it's only defined for 0, 2. So it's a quadratic going through 0 and 1, so normally the parabola would do this. But this one's only defined on the interval 0, 2, so we only start it here, and it's going to come up and do that. We can just see, just by staring at the picture, we can see that this point here will be our global maximum, and this here will be our global minimum. So sometimes the max and min occur at the endpoints, and sometimes they occur somewhere in between. It just depends on the problem. So we can see that this function f has a global maximum here at 2. So if I whack 2 into the formula here, I get 2 times 2 minus 1, which is just 2. So it has a global maximum of 2 at x equals 2. Now for the minimum, well, because it's a quadratic, you know that the turning point happens at the average of the roots. I'm sure that's a result you've seen before, that for a quadratic, the turning point occurs at the average of the two roots here. So 1 plus 0 is 1, divided by 2 is a half. So that's going to be a half there. So it's going to have a global minimum at x as a half. And if I put a half back into here, I get a half minus 1 is minus a half, times a half is minus a quarter. So this is going to be minus a quarter here. So it's got a global minimum of minus a quarter at x equals a half. So it's a very simple example of what we're doing here. Now, not all functions have these maxima and minima. So for example, if I draw the graph of the function y equals inverse tan x, you should know that this one from high school maths. Tan of x has asymptotes at pi on 2 and minus pi on 2, so inverse tan of x has asymptotes this way at pi on 2 and minus pi on 2. And you see this doesn't have any global maxima or minima on the real line, because the function's getting close, as you go up this way, the function's getting closer and closer to pi on 2, but it never actually gets there. It has a limit, but it never actually reaches pi on 2. So there's no global maximum. Later on, we'll talk about what happens at pi on 2. We're going to call that a least upper bound later on, but it has no maximum. It never actually reaches pi on 2. It gets as close as you like, but there's no global maximum for this function. And similarly, if you go this way, it's getting closer and closer to minus pi on 2 as you take bigger and bigger negative x values. And again, there's no global minimum. It never reaches minus pi on 2. It gets as close as you like, but it never reaches there. So not all functions have these global maxima and minima. And so we'd like a little theorem that tells us exactly when these things are going to happen. When are you going to have a global max and a global min? And we have here this very important theorem called the min-max theorem. So the two important theorems thus far, the intermediate value theorem we've done, and this second theorem, the min-max theorem, which is another very important theorem. It says, suppose that f is continuous on a closed interval. Now again, as I mentioned before, all of these theorems, they're like the ads on TV, conditions apply. And you've got to be careful with the conditions. So the conditions are here are that f has to be continuous, and the other key word here is closed. You've got to be continuous on a closed interval. If that happens, then money back guarantee, f has a global maximum and a global minimum on the interval AB. In other words, there are real numbers c and d somewhere in this interval, so that f of x is bigger or equal to f of c for all x, so this is the minimum, and f of x is less or equal to f of d for some d in this interval, and this is true for all x in the interval, so this is the maximum. Now I'm not going to give a proof of this. The proof of this in fact relies on some fairly important properties of real numbers. In fact, it's not a trivial proof. It's geometrically, it's fairly simple to see that it should be true, but the actual proof is complicated, and I'm not going to go through it here. So note that the result no longer true if we use open intervals or if the function is not continuous. So as I mentioned before, as with all these theorems, conditions apply. If you don't satisfy the conditions, then you don't get the conclusion. It's much the same when you're buying something. It always says conditions apply, and if you don't follow the conditions, well, there's no money back guarantee. So let me just quickly show you an example of what happens when you don't satisfy the conditions. So I'm going to explain why f of x equals 1 over x has no maximum or minimum on the interval minus 1 to 1, and it's got no maximum minimum on the open interval 0 to 1. Well, you'll say, but hang on, minus 1 to 1 is closed. Yes, but if you draw the graph of 1 over x, here's the graph of f of x is 1 over x on the interval minus 1 to 1. So we're just drawing this much of the picture. So on the interval minus 1 to 1, there's the graph, and you can see, of course, something terrible is happening at 0. As you go towards 0 from the positive side, this is zipping up to plus infinity, and as you go to 0 from the negative side, it's zipping down to minus infinity. So this function, f is not continuous. F is not continuous on the interval minus 1, 1. And you can see it's got no maximum because it goes up to infinity. There's no maximum and there's no minimum. And the reason the theorem failed was because the function was not continuous. So you need to have continuity to actually guarantee, even on a closed interval, to have a maximum min. On the other hand, if we look at f of x equals 1 over x now just on the interval 0, 1, so we just get this much, and we're excluding the endpoints. So there's an open circle here. We don't include the value at 1. And you can see again, it is continuous on this interval. Once you give me any finite, any number as close as you like to 0, then this will be continuous, but it's got no maximum. And similarly, it's got no minimum either because I excluded this point 1. And even though f of 1 would be 1, we're excluding 1. So it's got no minimum and it's got no maximum. And that's because because the interval now is not open. So f is not continuous, is not defined on a closed interval. So in using the theorem, you need the fact that the function is both continuous and you're on a closed interval. Otherwise, you can't make the conclusion that you want from that result. Now, as I said, the result is intuitively fairly obvious, but the proof relies on properties of the real numbers that we haven't yet introduced, and so I'll pass over this point. You should be able to state precisely the intermediate value theorem with conditions and the min-max theorem. And we'll continue this in the next recording.